Hello there, and welcome to Space Science Before Sleep, where the universe grows quiet, curiosity moves gently, and science takes its time beneath the stars. Tonight we're going to approach one of the blackest-looking clouds in the Milky Way and ask what may be hiding inside it beyond it, and behind the light it has removed from view. A content reference OISITE 0, index 0, as though someone has erased a portion of the night and forgotten to fill it back in. But this black shape is not an opening, it is matter. Cold gas and tiny grains of dust have gathered along our line of sight, absorbing and scattering so much visible starlight that the space behind them appears to vanish. The title calls it the darkest nebula in space, but astronomy offers no simple universal contest for darkness. A cloud can look darker or lighter depending on its thickness, its distance, the light behind it, the wavelength used to observe it, and the sensitivity of the telescope. So we will treat darkest as an invitation rather than a record and travel slowly into the science of a cloud that seems to contain nothing at all. From the room around you, darkness may feel like the absence of something. Turn off a lamp, close a curtain, and familiar objects disappear even though they remain exactly where they were. A dark nebula works through a similar trick, but on a scale large enough to cover thousands of distant stars in a single image. One especially striking example is Barnard 68, a compact dark cloud seen against the dense stellar background of the Milky Way. In visible light, its rounded silhouette appears remarkably smooth and nearly starless, like a drop of black ink resting on a page crowded with tiny lights. Yet the stars have not been removed. Most are simply hidden behind the cloud, while some foreground stars remain visible because they lie between us and the darkness. Already the image contains several distances folded into one flat picture nearby stars, the cloud itself, and a much larger galactic background. The universe, as usual, has declined to label the layers for our convenience. Before we drift any farther, I'd love to know where in the world you're listening from tonight and what time it is there. And if these slow journeys through space help you relax, learn something new, or simply feel a little less alone beneath the night sky, I'd be grateful if you like the video and subscribe to Space Science Before Sleep. It helps this quiet corner reach more curious minds who may need something gentle at the end of the day. And for tonight's question, which hidden cosmic place would you most like to see through an infrared telescope? Perhaps the center of a dark cloud, the dusty heart of the Milky Way, or the place where a new star is only beginning to warm its surroundings. There is no need for a technical answer. A simple destination is enough. Now let the room grow a little quieter. Settle into the pillow, allow your shoulders to loosen, and remember that none of the details ahead need to be held tightly. There is no test waiting at the end of the cloud. You can follow every idea, let some of them pass or fall asleep while the journey continues without you. We're going to ask several questions, but we'll take them one at a time. Why does this cloud appear darker than the space around it? What is the black material actually made of? Are there stars already shining inside, or only cold regions that may someday collapse? How can astronomers map an object that reveals itself mainly by removing light? What changes when we observe it in infrared or radio wavelengths? And when we finally speak of what lies behind the nebula, do we mean the far side of the cloud, the objects hidden within it, or the distant galaxy continuing beyond it? The simple question has quietly become three questions. That is a useful place to begin. A nebula is not automatically bright. The word simply refers to a cloud-like region of gas dust or both, and its appearance depends on how that material interacts with light. Some nebulae glow because energetic stars cause surrounding gas to emit radiation. Some reflect nearby starlight. A dark nebula does neither strongly enough to overcome the background it blocks. Its most visible feature is therefore a deficit, fewer stars, less glow, and a silhouette traced against whatever lies farther away. The cloud is made mostly of gas, much of it hydrogen, while dust contributes only a small fraction of the mass. But dust has an outsized influence on what our eyes can see. Each grain is microscopic, yet the path through the cloud may contain so many grains that visible photons are repeatedly absorbed or scattered away from our direction. No individual grain has to be impressive. Given enough distance and enough companions, even very small things can become excellent curtains. This is why the black region is already a measurement. Its shape tells us where obscuring material lies. The stars that remain faintly visible through its thinner edges can appear dimmer and redder because shorter wavelengths are generally removed more efficiently than longer ones. Toward denser regions, background stars may fade until ordinary visible light images record almost nothing. But almost nothing is not the same as no information. Astronomers can compare the colours and brightness of stars seen through different parts of the cloud, estimate how much light has been lost, and gradually draw a map of the material in front of them. The nebula becomes visible through the shadows it casts across the Milky Way. We have not yet looked inside it, and we have not yet seen what waits on the far side. For now we have learned the first essential truth. The dark shape is not a door into emptiness. It is a foreground world, quietly announcing its presence by hiding the universe behind it. And to understand how such a small amount of dust can erase so many stars, we must move closer to the grains themselves. The darkness of a nebula is built from things far too small to see. Not from one enormous object blocking the stars, and not from a solid wall suspended in space, but from an immense population of microscopic grains scattered through cold gas. Each grain may be tiny, yet the journey through a cloud can be so long that a beam of starlight encounters grain after grain before reaching us. Some photons are absorbed, others are scattered in new directions. By the time the surviving light leaves the cloud, it may be dimmer redder, or missing entirely from our line of sight. The black silhouette therefore comes from accumulation. A single grain would accomplish almost nothing. A cloud containing uncountable numbers of them spread across distances that resist ordinary intuition can remove a crowded field of stars from view. The universe rarely needs a solid barrier when patience and distance will do. Interstellar dust is not the familiar grey powder that gathers quietly beneath furniture, although the shared name is difficult to avoid. Cosmic grains are made from solid material forged, altered and recycled through generations of stars. Many contain silicate-rich minerals or carbon-bearing compounds, while the coldest grains may acquire thin coatings of frozen molecules. Their shapes are irregular, their sizes vary, and their exact composition changes from one environment to another. Dust contributes only a small portion of the total mass of a molecular cloud. Most of the matter is gas-dominated by hydrogen and accompanied by helium and trace amounts of heavier elements. Yet gas can be remarkably transparent at visible wavelengths, while dust interacts strongly with the light our eyes are built to detect. This gives the minority component control over the cloud's appearance. It is rather like allowing a small group of closed curtains to determine whether an entire house looks occupied from the street. The comparison is imperfect, of course. A curtain has a surface. A dark nebula is diffuse layered and crossed by light along countless different paths. When visible light enters such a cloud, two processes become especially important. Absorption occurs when a grain takes energy from an incoming photon. Scattering occurs when the photon is redirected rather than continuing toward the observer. Both can make a background star appear fainter, even though the star itself has not changed. Scattering also depends on wavelength. In many dusty regions, shorter visible wavelengths are removed more efficiently than longer red wavelengths. A star seen through the cloud may therefore appear redder than it truly is, much as the sun becomes orange or red when its light travels through a longer path in Earth's atmosphere near the horizon. The mechanisms are not identical in every detail, and interstellar grains are not simply a larger version of atmospheric haze, but the visual consequence is familiar. Blue light is reduced more strongly. Red light survives more easily. Astronomers call this effect interstellar reddening, and it is one of the clues that allows them to recognize dust even when the cloud itself produces almost no visible glow. The cloud does not make the absorbed energy disappear. Dust grains warmed by radiation release energy again, but often at wavelengths longer than the visible light they absorbed. In a dark nebula, much of this re-radiation emerges in the infrared or sub-millimeter part of the spectrum where cold material can glow without appearing bright to human eyes. This creates one of the quietest transformations in astronomy. A region that looks almost perfectly black in a visible light image may become structured and luminous when observed with instruments sensitive to longer wavelengths. The glow is usually faint and cold rather than brilliant. It can reveal warmer edges exposed to surrounding starlight cooler interiors, protected from that radiation, and compact regions where internal heating may be present. But changing wavelength is not a magical way of making every cloud transparent. Dense dust can remain opaque even to portions of the infrared spectrum. Different wavelengths reveal different depths, temperatures, and materials. There's no single pair of cosmic spectacles that solves everything at once. The behavior of the dust also depends on where it lives. Near the outside of a cloud, grains are more exposed to radiation from nearby stars and the wider galaxy. Deeper inside, the strongest external light has already been weakened, allowing temperatures to fall and chemical conditions to change. Grains may collide, gently stick together, acquire icy mantles, or become aligned partly by magnetic fields and radiation. These changes can alter how they absorb, emit, and polarize light. The cloud is therefore not made from one perfectly uniform kind of dust sprinkled evenly through space. It has layers, gradients, clumps, and histories. A grain near the illuminated edge may experience a very different environment from one buried near a dense core. This matters because astronomers often infer the amount of hidden material from the way light has been altered. If the grain properties change, the conversion from dimming to mass becomes less certain. The shadow remains informative, but it must be interpreted with care. From our distant viewpoint, all these interactions are compressed into a simple image. Stars around the cloud, fewer stars near its edge, and perhaps almost none toward the center. Yet every missing photon has followed a physical path. Some were scattered away and may be traveling elsewhere through the galaxy. Some were absorbed and later re-emitted as longer wavelength radiation. Some never encountered enough dust to be removed and continued toward a telescope. The black shape is therefore not merely a blank place on the sky. It is the visible result of countless encounters between light and matter accumulated across the depth of the cloud. Once astronomers understand how dust changes the brightness and color of background stars, they can begin to reverse the process. They can measure what has been lost, compare one line of sight with another, and turn a field of disappearing stars into a map. The darkness, having hidden the clouds so effectively, now becomes the very tool used to draw it. A dark cloud can be mapped by the stars it prevents us from seeing. This sounds almost contradictory, but the cloud does not need to shine in order to reveal its structure. It only needs a bright and crowded background. Along one line of sight, several stars may remain visible through a thinner outer layer. A little farther inward, those stars become fainter and redder. Near the densest center, many disappear from visible light images altogether. By comparing these neighboring regions, astronomers can estimate where the obscuring material is concentrated and how rapidly its thickness changes. The nebula becomes a silhouette with measurable depth, not because we can reach inside it, but because thousands of distant stars send light through different portions of the cloud. Each star acts like a tiny lamp placed behind an enormous curtain. Together, those lamps trace the curtain's folds. The simplest version of this method is called star counting. Astronomers examine a region of sky containing a dark cloud and count how many stars are visible in small areas across the image. They then compare those counts with a nearby region where the view is less obscured. If the background population is reasonably similar, a shortage of visible stars suggests that dust is blocking them. The idea is straightforward, though the real sky is not always cooperative. Stars are not distributed perfectly evenly, and some lie in front of the cloud rather than behind it. Others are naturally too faint to appear in the image even without dust. A brighter telescope may detect stars that a smaller instrument misses. Still, when many measurements are combined, the pattern becomes clear. The outer cloud allows more background stars through. The inner cloud allows fewer. A map begins to emerge from absence. Counting stars tells us where the cloud is thick, but stellar colours provide a more sensitive clue. Stars naturally come in different colours because their surface temperatures differ, yet astronomers can often estimate what a particular star's colour should be from its spectrum or from comparisons with similar stars. When its light passes through dust, shorter wavelengths are generally weakened more strongly than longer wavelengths. The star therefore appears redder than expected. By measuring this colour change known as colour excess, astronomers can estimate how much dust lies along the line of sight. One star provides only a narrow probe through the cloud. Hundreds or thousands of stars create a network of probes, each crossing a slightly different path. It is rather like studying a sheet of stained glass by placing many small white lights behind it and measuring how each light changes. The difference is that the cosmic sheet may be light-years deep, irregular, and moving. Barnard 68 offers a particularly clear example of this technique. In visible images, it appears as a compact rounded patch of darkness placed against a rich field of Milky Way stars. Its edges are not perfectly sharp. Stars near the outer boundary remain visible, though some are dimmed and reddened. Closer to the centre, the number of detectable background stars falls dramatically. By observing the cloud at wavelengths where more of those reddened stars can still be detected, astronomers have used their altered light to estimate how the obscuring material is distributed across the globule. The result is not simply a black circle with a border. It is a gradual increase in column density toward the interior, describing how much matter lies along each line of sight. Barnard 68 is useful because its silhouette is isolated and visually simple, but its true interior is still more complicated than the smooth outline suggests. An extinction map does not give us a direct three-dimensional picture. It measures the accumulated effect of material between the background star and the telescope. A dense, narrow clump can sometimes produce a similar amount of dimming to a longer path through thinner material. Both may remove comparable amounts of light while representing different shapes in space. The map is therefore closer to a shadow projection than a complete model of the cloud's interior. Imagine seeing the shadow of a closed hand on a wall. The outline reveals the hand's presence and some of its structure, but it cannot immediately tell you the exact position of every finger along the direction of the light. Astronomers must combine extinction with other evidence, including distance measurements, dust temperature, molecular emission, and internal motion. Even then, the cloud's full three-dimensional form usually remains partly reconstructed rather than directly seen. There are other complications hiding inside the apparently simple darkness. Some stars projected against the cloud may actually lie in front of it, and therefore show little or no reddening. Background stars may be located at many different distances, and may possess different intrinsic colours. Dust grains may also change in size or composition from the outer layers to the colder centre, altering the relationship between colour and total mass. In the most opaque regions, so few background stars remain detectable that the very method becomes less precise where the cloud is thickest. The curtain becomes difficult to measure once it hides nearly every lamp behind it. Astronomers respond by observing at longer wavelengths, where dust often blocks less of the incoming starlight. Near-infrared instruments can recover stars that have vanished from visible images extending the map deeper into the cloud. This is how a black patch is slowly converted into a scientific landscape. The missing stars mark the denser regions. The reddened stars measure the dust along individual paths. The remaining uncertainties remind us that an image of the sky compresses depth, distance, and structure onto one flat surface. Yet the method accomplishes something remarkable. It turns obscuration into information. The cloud hides the Milky Way, and the precise way it hides the Milky Way reveals the cloud in return. We can now draw its projected shape and estimate where its material thickens, but the stars behind it are still only faint messengers passing through the dust. To discover whether the cloud conceals warmer grains, embedded sources, or structures invisible to our eyes, we must change the kind of light with which we look. The cloud does not change when we look at it in infrared light. Our access to it does. A dark nebula that appears smooth and nearly empty in visible wavelengths may suddenly become crowded with stars crossed by faint structures or edged by glowing dust when an infrared instrument observes the same direction. This does not happen because the telescope has increased the brightness of an ordinary photograph. Infrared light is a different region of the electromagnetic spectrum, lying beyond the red end of human vision. Its wavelengths are longer than those our eyes can detect, and many of them interact with interstellar dust less strongly than visible light does. More infrared photons can therefore complete their journey through the cloud and reach the telescope. The black curtain begins to thin. Stars that seemed erased return as faint points, although they may still look reddened and dimmed. A cloud once defined by missing light becomes layered with background objects, foreground dust, and perhaps a few sources buried within it. It is helpful to imagine that visible and infrared observations are not two brighter or darker versions of the same photograph, but two different ways of sensing the same environment. A hand placed inside a closed bag may be hidden from your eyes while remaining easy to recognize by touch. Neither sense is false, each responds to different information. In a similar way, visible light is excellent for showing hot stars, illuminated gas, and sharply silhouetted dust, while near-infrared light can pass through some dusty regions more easily and reveal stars that remain concealed at shorter wavelengths. This is why images of star-forming clouds often transform so dramatically when the wavelength changes. A dark pillar or rounded globule may become semi-transparent. The empty-looking background fills with stars. Points of light may appear within the cloud itself. Yet the analogy has a limit. Infrared is not a single sense and not a single wavelength. It covers a broad range, and different portions of that range reveal very different physical conditions. Near-infrared observations are especially useful for recovering obscured stars. Their light may travel through more dust before being absorbed or scattered beyond detection, allowing astronomers to extend the extinction maps we began drawing in the previous part. Stars missing from a visible image can reappear in the near-infrared, providing additional lines of sight through denser sections of the nebula. Their colours still carry evidence of the dust they have crossed, so the cloud does not merely become transparent and surrender all its secrets. Instead, the available sample of background probes becomes larger. Some of the newly visible points may be ordinary distant stars located far beyond the cloud. Others may lie near its surface or within its depth. Separating these populations requires measurements of colour, brightness, distance, motion, and sometimes spectra. A point of light appearing inside the silhouette is therefore not automatically a newborn star. Projection is quite capable of placing unrelated objects together and leaving astronomers to sort out the seating arrangement. At longer infrared wavelengths, the story begins to change from transmitted starlight to radiation emitted by the dust itself. Grains that absorbed energy from surrounding stars do not remain permanently loaded with it. They release that energy again, often as infrared radiation suited to their low temperatures. The same material that appears black against visible starlight can therefore glow when observed in the far infrared. Warmer dust may shine more strongly at shorter infrared wavelengths, while colder material becomes prominent farther along the spectrum and into submillimeter wavelengths. Because telescopes translate this invisible radiation into colours, our eyes can view, the final image may contain luminous reds, golds, blues, or greens that are not the colours a human observer would see while floating nearby. They are visual guides to wavelength and intensity. The cloud has not become brightly painted. The image has given invisible measurements of visible language. These longer wavelength maps can reveal that an apparently simple nebula is anything but simple. A black outline may contain temperature variations, compact concentrations, curved edges, branching structures, or narrow threads of denser material. Regions warmed from outside can differ from sheltered interiors. A deeply embedded young source when present may heat nearby dust and create a concentrated infrared glow, even while remaining invisible in ordinary light. In other clouds, no internal heating source appears. Their faint emission comes mainly from cold dust responding to the general radiation of the surrounding galaxy. That difference matters. Infrared brightness alone does not prove that a star is being born, just as darkness alone does not prove that nothing is there. Astronomers compare several wavelengths to estimate temperature and determine whether a bright region is warm, unusually massive, externally illuminated, or heated from within. One image offers a clue. A sequence of wavelengths begins to offer an explanation. Even infrared light has limits. The densest parts of a dark nebula may absorb near-infrared radiation strongly enough to conceal whatever lies behind them. At some wavelengths, Earth's atmosphere also absorbs much of the incoming infrared signal, or produces its own infrared glow, which is one reason cold telescopes above the atmosphere have been so valuable. Longer wavelengths may reveal cold dust, but provide less sharply detailed images than shorter wavelengths, depending on the telescope and instrument. Foreground material can overlap with the cloud, and warmer dust can outshine colder structures along the same line of sight. There is no wavelength at which every layer politely separates itself from every other one. Astronomy proceeds instead by combining partial views, visible shadows, near-infrared stars, mid-infrared warmth, and far-infrared emission from colder grains. Together they open the curtain, but they do not remove it. By changing wavelength, we've recovered hidden stars and watched the dark material begin to glow. We can estimate where the dust is colder, where it is warmer, and where an embedded source might be adding energy from within. But dust is only the small component that controls the cloud's appearance. Most of the mass is gas, and much of that gas remains difficult to recognize in an infrared image alone. It has its own temperatures, motions, and chemistry. It can contract, expand, rotate, collide, or flow along structures that a dust map only partly reveals. To follow that larger reservoir, astronomers must stop relying only on pictures and examine narrow fingerprints carried by radio and millimeter waves. The cloud has allowed us to see through portions of its curtain. Now we must listen to the molecules moving in the dark. A dark cloud does not need visible light to announce that it is moving. Its molecules carry narrow signatures at radio and millimeter wavelengths, and within those signatures are clues to temperature, density, chemistry, and motion. When astronomers point a radio telescope toward a nebula that looks almost perfectly black, the result is not an ordinary photograph. It is a spectrum, a measured spread of radiation, arranged by wavelength or frequency. Most of that spectrum may appear quiet. Then, at particular frequencies, narrow peaks rise from the background. Each peak belongs to a specific transition within a particular kind of molecule. The cloud has not begun speaking in any literal sense, but the comparison is useful. Visible images show where the dust blocks light. Spectral lines reveal what some of the gas is doing inside that darkness. Most of the molecular gas is hydrogen, usually in pairs of atoms joined as molecular hydrogen. Yet cold molecular hydrogen is surprisingly difficult to observe directly under the conditions found inside many dark clouds. It is abundant, but its common transitions are not easily excited at such low temperatures, and the molecule lacks some of the features that would make it a convenient radio beacon. Astronomers therefore rely on other molecules as tracers. Carbon monoxide is especially important because it is relatively abundant, produces detectable rotational transitions, and often occupies the same broad regions as molecular hydrogen. When carbon monoxide molecules rotate, they can shift between allowed energy states and emit radiation at precise millimeter wavelengths. Detecting that radiation tells us that molecular gas is present, although converting the signal into a total amount of hydrogen requires assumptions about temperature abundance, optical depth, and local chemistry. Carbon monoxide is a guide, not a complete census. Other molecules help reveal denser or chemically different regions. Some spectral lines become useful only where particles collide often enough to excite them, allowing astronomers to distinguish broad cloud material from compact dense cores. Different tracers may highlight outer layers, shielded interiors, shocked gas, or regions where particular chemical reactions have become favorable. The resulting maps can look remarkably unlike one another, even when they cover the same nebula. One molecule may spread across much of the cloud, another may appear only in small knots. A third may weaken near the coldest center because it has frozen onto dust grains or been transformed by chemical reactions. This is why a molecular map should not be mistaken for a direct photograph of all the gas. It is more like entering a dark building and hearing different machines through the walls. One sound may come from the ventilation system, another from a refrigerator, and another from footsteps in a distant room. Their locations tell us something, but no single sound describes the entire building. A spectral line also records motion through the Doppler effect. If gas is moving toward us, its line shifts slightly toward a higher frequency. If it is moving away, the line shifts in the opposite direction. The changes are small, but modern instruments can measure them precisely enough to reveal motion within a cloud that appears completely still in the sky. Different regions may move at different speeds. Gas may stream along a filament, rotate around a dense center, contract inward, expand outward, or churn through turbulence. Several clouds at different distances can even overlap along the same line of sight, while moving at different velocities, allowing their spectral signals to be separated when an ordinary image blends them together. The night sky compresses distance onto a flat surface. Velocity gives astronomers another way to pull some of those layers apart. Interpreting these motions is not always simple. A broad spectral line may indicate turbulence, but it can also contain unresolved flows or several overlapping components. A line with two peaks might suggest expanding or collapsing material, yet the result depends on how opaque the tracer is and how temperature changes through the cloud. Rotation can resemble a gradual velocity shift across a map, though similar patterns may be created by larger flows or unrelated structures projected together. Astronomers therefore compare several molecular lines, including tracers that respond differently to density and opacity. They also combine the spectra with dust maps, temperature estimates, and models of radiative transfer, the process by which radiation is emitted, absorbed and scattered before reaching the telescope. The cloud is not offering a simple recording of its interior. It is sending a signal that has already passed through the very material we're trying to understand. Chemistry adds another layer of quiet complexity. Deep inside, a dark nebula, temperatures may fall low enough for molecules to adhere to dust grains and form icy mantles. When an important tracer freezes out of the gas, its emission may weaken near the densest region, even though the total amount of matter continues to increase. A molecular map could therefore show what looks like a hollow center, where the cloud is actually most concentrated. Cosmic rays passing through the cloud can ionize particles and support chemical reactions even where ordinary starlight has been greatly reduced. The interior is dark and cold, but it is not chemically inactive. Atoms and molecules collide, exchange, partners settle onto grains and sometimes return to the gas. These processes influence which traces remain detectable and how accurately each one follows the hidden mass. By combining molecular fingerprints, astronomers can begin to reconstruct a cloud as a changing physical environment rather than a flat black silhouette. The strength of a line may help constrain temperature or density. Its shape can reveal opacity and internal motion. Its exact frequency identifies a molecule. Its position on the sky shows where that molecule is emitting. None of these clues works perfectly alone, and some of the most abundant material remains indirectly measured, but together they transform the darkness into a layered map of gas motion and chemistry. We now know that the cloud is not merely sitting in front of the stars. It has an interior life of slow collisions and hidden currents, all continuing at temperatures where human experience offers few useful comparisons. To understand what happens as external starlight weakens and this molecular world becomes colder, we must leave the illuminated edge behind and move deeper into the protected interior. The deeper we move into a dark molecular cloud, the less the surrounding galaxy can reach us in its familiar form. Near the outer boundary, ultraviolet light from distant stars still penetrates the gas-breaking fragile molecules apart, and keeping much of the hydrogen in individual atomic form. Farther inward, dust absorbs more of that radiation, and the cloud begins to protect its own interior. The change is gradual rather than marked by a clear surface. There is no doorway where atomic space ends and a molecular world begins. Instead, the balance shifts layer by layer. Destructive radiation weakens. Molecules survive longer. Temperatures fall. The chemistry becomes quieter and more complex. A place that looked like one smooth black patch from outside now reveals itself as a sequence of environments, each shaped by how much light has managed to reach it. Molecular hydrogen, the most abundant molecule in these clouds, forms largely with the help of dust grains. Two hydrogen atoms wandering through the gas are not always able to join easily, and release the excess energy required to remain together. A grain provides a temporary meeting place. Atoms land on its surface, move across it, encounter one another, and may leave as a hydrogen molecule. The dust is therefore more than an obstacle that blocks our view. It is also a platform for chemistry. Once enough molecular hydrogen has accumulated, the cloud becomes better able to shield itself, because both dust and molecules absorb radiation that would otherwise break newly formed molecules apart. The interior grows increasingly protected. This is not a perfectly sealed shelter. Radiation still enters at some wavelengths, particles still move through the gas, and disturbances can arrive from outside. But compared with the exposed edge, the center can become remarkably isolated from ordinary starlight. As the radiation weakens, the temperature drops. In many dense cloud interiors, the gas and dust may remain only a small number of degrees above absolute zero. Human experience offers almost no direct comparison for such cold, because even the coldest winter air is warm by molecular cloud standards. Yet the cloud is not frozen into a solid block. Its density is still extraordinarily low compared with the air in a room. Molecules may travel considerable distances between collisions, and the entire region remains a thin gas spread across an enormous volume. This combination can feel strange, a cloud dense enough to hide the stars yet still far emptier than any vacuum most people encounter on Earth. The darkness comes not from compact solidity, but from the accumulation of sparse material over a path that may extend for light years. Space has room to make very little add up to quite a lot. At these low temperatures, dust grains begin to collect delicate icy mantles. Molecules such as water, carbon monoxide, carbon dioxide, methane, ammonia, and other simple compounds may adhere to grain surfaces depending on the local conditions. The word ice may suggest a visible frost, but these coatings are microscopic, forming layer by layer on particles already too small to see. Within them, atoms and molecules can meet and react in ways that may be difficult in the thin gas. Radiation and energetic particles can alter the frozen material, creating new chemical combinations. Some products remain trapped until a later period of warming releases them. In this way, the cold interior can store chemical history. It is not manufacturing life, and the presence of carbon-bearing molecules is not evidence of biology. It is simply demonstrating that complex chemistry does not require warmth, sunlight, or a planet. Even in darkness, matter continues arranging itself. One source of activity reaches the cloud even when ordinary starlight has been greatly reduced. High-energy particles known as cosmic rays can pass deep into regions that visible and ultraviolet radiation cannot easily penetrate. When they strike atoms or molecules, they can remove electrons and create ions, which are especially reactive chemical partners. These ionized particles help sustain networks of reactions in places that would otherwise be extremely quiet. Cosmic rays may also influence how strongly the gas couples to magnetic fields and can provide a small but persistent source of heating. Their exact intensity inside different clouds is not always easy to determine, and the phrase cosmic ray covers particles arriving from a variety of energetic environments. Still, their role carries a gentle contradiction. The most protected part of the nebula is never completely isolated. Events elsewhere in the galaxy continue to send particles through it, maintaining a faint chemical pulse in the dark. The cloud's interior also changes the behavior of the tracers astronomers use to study it. A molecule that glows reliably in the outer regions may freeze onto grains near the center and nearly disappear from the gas. Another molecule may become more abundant because the local chemistry favors its survival. Gas and dust temperatures may begin to follow one another more closely, where densities rise and collisions become more frequent. Meanwhile, the cloud is never perfectly still. Weak turbulence, slow flows, magnetic forces, external pressure and gravity continue to rearrange its material. A region can be cold without being calm, and calm without being permanent. The apparent silence of the nebula is partly a limitation of our senses and partly a reflection of how slowly its processes unfold. From inside this imagined descent, the visible Milky Way has almost vanished. The surrounding dust has screened away much of the external light, and there may be no internal star to replace it. Yet the darkness now feels different from the empty silhouette we first approached. It contains molecular hydrogen assembled on grain surfaces, icy mantles holding chemical records particles stirred by cosmic rays, and gas moving through magnetic and gravitational fields. The interior is not a featureless chamber. As telescopes map it with greater sensitivity, the cloud begins to separate into elongated filaments, broader clumps and compact cores where the density rises still further. Some of these structures may disperse, some may remain supported, and a few may become the places where gravity finally gathers enough patience to begin building a star. The cloud is not a smooth darkness, it is a landscape seen from too far away. When observations at far infrared and submillimeter wavelengths reveal the glow of cold dust, the apparently simple silhouette breaks apart into a tangled network of elongated structures. Some stretch across large portions of the cloud like faint threads. Others gather into broader concentrations or tighten into compact knots. Astronomers describe these structures with words such as filaments, clumps, and cores, but the boundaries between them are not marked by sharp surfaces. They are categories used to organize a continuous and complicated distribution of matter. A filament is generally longer than it is wide. A clump is a broader concentration that may contain enough material to form several stars. A core is smaller and more compact, often discussed as the immediate environment from which one star or a small system might eventually emerge. The terms are useful, but the universe has not signed an agreement to keep every cloud neatly inside them. Filaments are among the most striking features of cold molecular clouds. Some appear as long, gently curved bands of dust and gas. Others branch, intersect, or connect to thinner structures extending into the surrounding material. From a distance, the cloud may resemble a dark, forested hillside. Only when the view sharpens do separate ridges, valleys, pathways, and individual clusters of trees become visible. In the nebula, however, these apparent threads are not solid ropes. They are regions where more matter lies along a particular path, producing stronger extinction, or brighter, long-wavelength dust emission. Their true shapes may be cylindrical, flattened, twisted, folded, or partly assembled from structures that overlap in projection. A narrow line on a map might represent one coherent filament, or several unrelated layers placed along the same line of sight. The image gives us a pattern on the sky. Spectral measurements are needed to determine whether the gas within that pattern is also connected in distance and velocity. Some filaments contain compact concentrations arranged along their length. This can create the visual impression of beads threaded onto a string with dense cores appearing at intervals inside the elongated cloud. Many observed young stars and candidate prestellar cores are associated with dense filaments, suggesting that these structures often provide favorable places for matter to gather. A filament may collect gas from its surroundings, channel material along its length, or become unstable and divide into denser sections. Yet this is not a universal assembly line. Some filaments contain few compact cores. Some appear too diffuse to collapse under their own gravity. Star formation can also occur in environments whose filamentary structure is weak, unresolved, or difficult to identify. The connection is important without being absolute. A filament is better understood as a possible route towards stellar birth than as a promise that a star is already on its way. As we move towards smaller scales, the language becomes more closely tied to interpretation. A dense core is a compact region whose density exceeds that of its surroundings, but density alone does not reveal its future. If no embedded young stellar object is detected, the core may be called starless. That word describes an observation no internal protostar has yet been found with the available instruments. It does not necessarily mean the core is empty, motionless, or permanently incapable of forming a star. A prestellar core is a more specific idea. It is a starless core believed to be gravitationally bound and therefore considered a likely precursor to collapse. If a central protostar is detected, the region becomes a protostellar core. These labels sound like orderly steps, but astronomers must infer them from incomplete evidence. A very faint source might escape detection. A core thought to be bound may have an uncertain mass or temperature. Improved observations can therefore change the name without changing the object itself. Clumps occupy a somewhat larger scale, and may contain networks of cores rather than one isolated stellar seed. In quieter regions, a compact Bok globule may hold only one or a few dense centers. In large molecular cloud complexes, a massive clump can provide the material for an entire group or cluster of stars. Within it, several cores may evolve at different rates. One may remain starless while a neighbor already contains a protostar. Another may be disrupted by internal motion or by activity from nearby young stars. The nested structure can continue upward and downward, a core inside a clump, the clump inside a filament, the filament inside a molecular cloud, and the cloud inside the wider interstellar environment of the galaxy. These levels help astronomers discuss scale, but they do not behave as sealed boxes. Matter can flow between them. Radiation can heat their edges. Magnetic fields can cross several layers. Gravity can act locally while the larger cloud continues to move around it. The maps also remind us that density is not destiny. A compact knot may look like the beginning of a star, yet it can remain supported by internal pressure, magnetic forces, or motion. It may be compressed temporarily and then expand again. Two features may overlap in an image without interacting physically. Even the apparent boundary of a core depends partly on the tracer wavelength sensitivity and method used to identify it. One survey may divide a region into several objects, while another treats the same emission as one extended structure. This does not make the observations useless. It means the cloud is continuous while our categories are practical tools. A shoreline can still be mapped even when every wave redraws part of its edge. The important question is not merely whether a dense structure exists, but whether it is held together strongly enough for gravity to overcome the forces resisting contraction. We have now moved from a black patch to a layered architecture, broad cloud material branching filaments, denser clumps and compact cores hidden inside them. Some cores contain no detectable internal source. Some may be approaching collapse. Others already shelter protostars that remain invisible in ordinary light. But the appearance of a dense core does not tell us which future it will choose. Inside every candidate stellar birthplace, gravity pulls matter inward, while heat, turbulence, rotation, magnetic fields and pressure complicate the movement. The cloud may contract, fragment, oscillate or disperse. To decide whether one of these dark knots can become a star, we must pause at the place where structure becomes struggle and watch gravity meet everything standing in its way. A dense core is not a star waiting for someone to press a switch. It is a temporary arrangement of matter whose future depends on a slow and complicated contest. Gravity pulls inward because every part of the core attracts every other part. Thermal pressure pushes back because particles are always moving even in extreme cold. Turbulent motions stir the gas on many scales. Magnetic fields guide charged particles and influence the motion of the mostly neutral material around them. Rotation can redirect some inward movement into circulation, while pressure from the surrounding cloud can squeeze the core from outside. None of these influences acts alone, and none behaves like a hand placed neatly on one side of a balance. They overlap change with time and reshape the very object they are regulating. The question is not simply whether gravity is present. Gravity is always present. The question is whether the core can resist it for another quiet interval. Thermal pressure provides the most familiar form of resistance. Even a cold gas contains particles moving in many directions, colliding and spreading their momentum through the core. Compress the gas and those collisions become more frequent. The internal pressure rises, opposing further compression. A small warm diffuse concentration may therefore disperse rather than collapse. A larger or colder concentration may be unable to support its own weight. Astronomers often describe this through a competition between internal support and self-gravity, though real cores rarely have one uniform temperature or a perfectly simple shape. The basic image is similar to a cushion supporting a weight. The material inside pushes outward as the load presses inward. But a molecular core has no fabric cover, no solid boundary, and no fixed amount of gas. Matter can enter leave-cool heat or rearrange itself. The cushion is changing while the weight is still being measured. Turbulence makes the picture less orderly. In everyday language, turbulence suggests violent disorder, but inside a dark cloud it can include motions that are slow by earthly standards and still fast compared with the local speed of sound. These motions broaden molecular spectral lines and create a shifting pattern of density variations. Turbulence can provide a form of support by continually moving gas and preventing the entire cloud from settling inward at once. Yet the same turbulence can drive streams of material together, compressing gas into filaments and dense knots, where gravity becomes more effective. It can delay collapse in one region while helping create the conditions for collapse in another. This is why calling turbulence an opponent of gravity is only partly correct. It is more like restless traffic in a city. Movement can keep one square from becoming crowded, then funnel vehicles into another street until a jam forms there instead. The cloud is never merely stirred, it is reorganized. Turbulence also fades unless something continues to drive it. Motions can lose energy through shocks and collisions, converting organized flow into heat that is later radiated away. Larger galactic processes may replenish some of that motion-expanding bubbles around stars, stellar winds, supernova remnants, gravitational flows, or the movement of the cloud through its environment. Within a particular quiet core, however, the origin and persistence of the measured motion may be difficult to determine. A broad spectral line might represent genuine turbulence, unresolved inflow, several overlapping layers, or a mixture of all three. The core does not provide labels for its internal currents. Astronomers compare different molecular traces and map how velocity changes across the object, looking for patterns consistent with contraction rotation, random motion, or external disturbance. Even then, several interpretations may survive. A cloud can look calm in one molecule and unsettled in another because each tracer samples a different part of the interior. Magnetic fields add an influence that cannot be seen directly in an ordinary image. Interstellar space contains charged particles, and their motion is affected by magnetic fields threading the gas. Most particles in a cold molecular cloud are neutral, but collisions with the smaller ionized population allow the magnetic field to influence the wider material indirectly. If the field is sufficiently strong and well arranged, it can resist motion across its lines, alter the direction in which gas flows and slow contraction. Matter may travel more easily along the field than across it, encouraging flattened or elongated structures rather than perfectly spherical collapse. But magnetic support is not an invisible cage. Neutral particles can gradually drift relative to charged particles. Field lines can bend and gravity can become strong enough to pull material inward despite the magnetic resistance. The field shapes the journey. It does not necessarily forbid the destination. Astronomers infer magnetic field orientation partly through polarization. Elongated dust grains can become statistically aligned with the local field, causing the light they absorb or emit to carry a preferred orientation. By mapping this polarization across a cloud, researchers can draw projected patterns that suggest how the magnetic field lies across the sky. Smooth-ordered patterns may indicate that the field has remained influential despite turbulence. Distorted or pinched patterns may suggest that gravity or large-scale flows have dragged the field with the gas. Yet these maps show only a projection, and the true three-dimensional geometry may be more complicated. The field can point partly toward or away from us. Several layers may overlap, and the efficiency with which grains align may change in dense interiors. A beautiful pattern of lines is therefore not a complete magnetic blueprint. It is another shadow of the hidden structure. External pressure and rotation further complicate the fate of the core. Gas surrounding a compact region can press inward, helping confine material that might otherwise expand. A passing shock or collision between flows may compress the core temporarily, perhaps pushing it closer to gravitational instability. Rotation, meanwhile, can prevent all the matter from falling directly toward one point. As the core contracts, even a modest initial spin can become more important, much as a slowly turning skater rotates faster when drawing inward. Later, this angular momentum may contribute to the formation of a disk or to fragmentation, but at the starless stage the movements can be subtle and difficult to separate from turbulence. What appears to be one contest is really a network of exchanges. Gravity strengthens as density rises, cooling reduces thermal support, compression changes the magnetic field, and turbulence creates new concentrations while fading elsewhere. So where are we now? We are inside a cold core that may be dense, chemically rich, magnetized and slowly moving, yet still contain no star. Its future cannot be read from darkness alone. If gravity gains a lasting advantage, contraction may continue toward a protostar. If internal and magnetic support remain sufficient, the core may linger near balance. If external conditions change or turbulent motions pull it apart, it may disperse back into the wider cloud. A single observation gives us only one moment in a process that may unfold across times far longer than a human life. This is why some of the most interesting objects in a dark nebula are not the ones already shining. They are the silent cores balanced near an uncertain threshold. And among them, Barnard 68 offers a particularly gentle puzzle, a dense, rounded darkness that has been studied closely, yet may remain starless for longer than the simple story of stellar birth would lead us to expect. Barnard 68 appears almost too simple. Against the crowded background of the Milky Way, it forms a compact and rounded silhouette, with none of the brilliant knots or glowing edges that usually make a nebula look active. No young star has been securely revealed at its centre. No obvious jet pierces its surface. No internal lamp warms the cloud strongly enough to announce a protostar. Astronomers therefore describe it as starless, but that small word is easy to misunderstand. It does not mean the cloud contains nothing. It does not mean that it has never changed or that it will remain unchanged forever. It means that observations have not identified an embedded young stellar object within it. Barnard 68 is filled with cold gas-dust chemistry, pressure, magnetic influence and internal motion. It contains nearly everything required for a stellar beginning except the beginning itself. For now, the cloud remains dark on both sides of the threshold. Its rounded appearance once encouraged a particularly elegant interpretation. The density rises gradually toward the centre, in a pattern resembling a theoretical cloud held near equilibrium by the balance between its own gravity and pressure from within and around it. In this picture, Barnard 68 is neither freely expanding nor rapidly collapsing. It is confined cold and close to a critical condition. Add enough mass, reduce enough support, or increase the pressure around it, and gravity may gain the advantage. Leave the balance undisturbed and the core may persist. This theoretical description is useful because it allows astronomers to compare a real cloud with a simplified physical model. But the model assumes a smoother and more orderly object than nature is required to provide. Barnard 68 is not a perfect sphere suspended in a perfectly uniform environment. Its edges contain structure, its temperature changes with depth, and its internal gas does not remain completely still. Molecular spectra have revealed motions that complicate any simple picture of collapse. In some portions of the cloud, gas appears to be moving inward. In others, the inferred motion points outward. Different layers may therefore be travelling in different directions at the same time. One explanation is that the core is oscillating around a roughly stable configuration. Imagine a quiet bowl of water after the table has been nudged. The surface rises in one place, falls in another, and continues moving after the original disturbance has passed. Barnard 68 is not a liquid bowl, and its motions involve gravity-pressure chemistry and radiation passing through a three-dimensional cloud. Still, the image captures an important possibility. A core may breathe inward and outward without committing itself to complete collapse. Motion is not always departure, and inward motion is not always the first irreversible step toward a star. These possible oscillations also challenge the idea that every dense core is merely waiting through a brief pause before formation begins. If Barnard 68 has remained near equilibrium long enough for its chemistry and structure to develop, then some starless cores may be comparatively long-lived. They can be disturbed by changes in external pressure flows, in the surrounding gas-weak shocks, or interactions with nearby material, and then respond with waves that travel through their interiors. Some disturbances may fade, others may strengthen. A core can approach instability, move away from it, and approach again. This makes the cloud less like an egg inevitably preparing to hatch, and more like a sheltered hill of snow whose future depends on temperature, pressure, added weight, and the shape of the ground beneath it. The hill may slide, it may settle more firmly, it may also erode before anything dramatic occurs. There is, however, another interpretation of Barnard 68's uneven outer structure. Observations have suggested that a smaller concentration of material may be interacting with the main globule. Numerical models have explored whether such an encounter could add mass or disturb the cloud enough to trigger eventual collapse. Under that scenario, Barnard 68 would not remain starless indefinitely. The interaction could push a previously balanced object beyond its stable limit, leading it toward the formation of one or more low-mass stars. This is a plausible model, not a witnessed future. Astronomers cannot place a camera beside the cloud and wait through hundreds of thousands of years to confirm the prediction. They compare its present shape and motion with simulations, then ask which history produces the closest match. Other conditions or structures could produce some of the same clues. The cloud's next chapter remains inferred from a single page. The uncertainty is not a weakness in the science, it is the scientific result. We know that Barnard 68 is cold, dense, highly obscuring, and without a clearly detected protostar. We know that its internal molecular signals are more complicated than a uniform inward collapse. Evidence supports the possibility of oscillation, while other modelling suggests that interaction with nearby material could eventually destabilize it. What we do not know is whether the core will become a star, divide into several condensations, linger near balance, or lose material back to its surroundings. Even the label prostellar must be used carefully. A prostellar core is not merely starless. It is a core believed to be gravitationally bound and likely to progress toward collapse. Determining that status requires estimates of mass, temperature, pressure, geometry, and internal motion, each carrying its own uncertainty. For the moment, Barnard 68 remains a dark object hiding no detected stellar flame. Its significance lies partly in that absence. A glowing protostar would tell us that collapse had already crossed an important threshold. A starless core allows astronomers to study the conditions before that decision becomes clear. Here, gravity has gathered matter, but may not yet control its future. Pressure still answers. Magnetic fields may still redirect motion. The cloud may be oscillating after an old disturbance or moving toward a change that no human lifetime will witness. It waits without truly being still, and elsewhere inside darker clouds the balance does finally shift. Matter continues inward, the center grows denser and warmer, and gravitational energy begins to create a hidden source of light. The starless silence gives way very slowly to a protostar turning on in the dark. A protostar does not switch on in a single clean moment. There is no sudden point at which a dark core flashes like a lamp and becomes a completed star. Instead, gravity gradually changes the meaning of the darkness. Material that once drifted through the core begins moving inward more persistently. The central region grows denser, collisions become more frequent, and the gas has increasing difficulty releasing its energy. What began as a cold concentration develops a warmer and more compact center. At first, much of that warmth can still escape through radiation. As the density rises, however, the interior becomes increasingly opaque, trapping energy more effectively and slowing the collapse. A small central object begins to take shape inside the surrounding envelope. It is still gathering most of its final mass and has not begun the stable hydrogen fusion that defines an ordinary main sequence star. Yet it is no longer merely a starless core. A protostar has begun. The new object shines because collapse releases energy. Gas falling inward loses gravitational potential energy much as an object descending toward Earth gains speed. Near the protostar, some of that motion is converted into heat through compression, collisions, shocks, and the process of joining the growing central body. The protostar itself also contracts, releasing additional gravitational energy. This early luminosity can be substantial even before sustained hydrogen fusion begins in the center. A covered lamp offers a useful image provided we remember its limits. The protostar is not powered by electricity, and its covering is not a solid shade. It is a warm, growing object buried within a vast envelope of infalling gas and dust. Much of the light it produces cannot travel directly outward at visible wavelengths. The surrounding material absorbs that radiation warms slightly, and releases the energy again at longer wavelengths. The cloud therefore remains dark to human eyes, while becoming brighter to infrared instruments. In visible light, the protostar may be completely concealed. In the infrared and submillimeter spectrum, its presence can emerge as a compact warm source surrounded by colder emission. Astronomers examine how much energy arrives at different wavelengths, constructing a spectral energy distribution that helps them distinguish an internally heated object from a cold, starless core. A core warmed only from outside tends to remain coldest near its protected center. A protostellar core can show the opposite clue, a hidden central source heating nearby dust from within. Even then, the interpretation requires care. Background galaxies, foreground stars, temperature variations, and unrelated structures can sometimes appear in the same line of sight. A faint infrared point is evidence to investigate, not an automatic birth announcement. As material continues falling, it rarely travels directly into the center from every direction. The original core possesses at least a small amount of angular momentum inherited from turbulence, larger cloud motions, or rotation. As the cloud contracts, that motion becomes increasingly important. Matter spirals inward and begins gathering into a flattened, rotating disk around the protostar. The effect resembles a skater turning more rapidly after drawing inward, although a collapsing cloud is not a rigid body, and its angular momentum is continually redistributed. Magnetic fields, gravitational interactions, turbulence, and developing outflows can transfer some rotation through the system. The disk becomes a route by which matter moves toward the protostar rather than simply orbiting forever. Gas and dust travel through it, lose energy and angular momentum, and are gradually accreted by the central object. The protostar grows from material delivered through a changing and often uneven structure. Accretion may not proceed at a steady pace. Material can gather in the disk and then move inward in episodes, temporarily increasing the protostar's luminosity. A young object may brighten as a larger amount of gas falls onto it, then fade when the delivery rate decreases. Because the surrounding envelope absorbs and reprocesses much of this energy, changes can spread outward as waves of heating through the dust. Astronomers have observed young stellar objects whose infrared brightness varies, suggesting that stellar growth can occur in bursts rather than through one perfectly smooth flow. This matters because a single observation captures only one stage of an irregular process. A faint protostar might be in a quiet interval rather than permanently weak. A bright one might be experiencing an unusually active episode. Stellar birth, like the cloud that supports it, is less cooperative than the tidy arrows in a diagram. The protostar itself continues evolving while it gains mass. Its center becomes hotter and denser, and its internal structure changes as gravity compresses it. Some nuclear reactions may occur during these early stages, but the object has not yet reached the long-lasting balance associated with stable hydrogen fusion on the main sequence. It is still strongly shaped by accretion, contraction, and interaction with the surrounding disk and envelope. Its final mass is not yet settled. Some of the original core will join the star. Some may remain in the disk. Some will be redirected into outflows or dispersed into the wider cloud. If the core fragments, more than one protostar may develop, turning one dark condensation into a binary or multiple system. The birth of a star is therefore also the division of a cloud's material among several possible destinations. From outside, the nebula can continue to look almost unchanged. Its silhouette may remain black, its visible boundary calm, and its background stars hidden exactly as before. Yet inside, the physical story has crossed an important threshold. Gravity has produced a compact source that warms its surroundings, gathers material through a disk, and releases energy as matter descends toward it. The cloud is no longer merely storing the possibility of light. It contains an object actively growing towards stellar life. But the protostar does not remain sealed indefinitely. Rotation and magnetic processes near the disk help launch narrow jets, while broader flows carry material away from the center. These motions begin opening cavities through the envelope, creating paths along which radiation can travel more freely. The first light does not escape equally in every direction. It finds the openings carved for it. The first light from a protostar rarely escapes as a perfect sphere. The young object remains surrounded by a thick envelope of gas and dust, while a rotating disk occupies the crowded region near its center. Along most directions, radiation meets enough material to be absorbed and released again at longer wavelengths. But above and below the disk, the system begins to clear narrower routes through its surroundings. Fast jets travel outward from the central region, and broader flows of gas accompany them. Together, these motions push into the envelope sweep material aside and gradually create two opposing cavities. The protostar may still be invisible when viewed through the thickest part of the cloud, yet its light can travel much farther along these lower density paths. Stellar birth begins to reshape the curtain that concealed it, not by drawing it open evenly, but by making two small openings in a very large and complicated room. The narrowest structures are called jets. They consist of fast-moving material launched from the region close to the protostar, and its disk often extending in opposite directions along a common axis. Rotation and magnetic fields are thought to play central roles in lifting, accelerating, and guiding this material, although the exact details vary among models and remain under investigation. The jet axis is commonly oriented roughly perpendicular to the disk, where the path outward offers less resistance than movement through the dense disk itself. This arrangement also helps the growing system manage angular momentum. Matter in the disk cannot simply fall inward, while keeping all its rotational motion unchanged. Jets' wind's magnetic stresses and internal disk processes can carry some angular momentum away, allowing other material to continue toward the protostar. The system grows partly by ejecting. Cosmic construction, it seems, also produces a considerable amount of material that does not remain in the finished object. A jet is usually narrower and faster than the broader molecular outflow surrounding it. As the jet pushes into the cloud, it can transfer momentum to colder gas, drawing that material outward in two widening lobes. The result is known as a bipolar outflow, because it extends on opposite sides of the central source. These lobes may contain swept-up molecular gas that was once part of the surrounding core and envelope. Where the moving material collides with slower gas, shocks compress and heat the region. Molecules become excited and emit radiation that telescopes can detect at infrared millimeter or radio wavelengths. Bright knots and curved bow-shaped features may appear along the route, marking episodes of ejection, or places where the flow has met denser material. The pattern can resemble a narrow stream entering still water and spreading turbulence around itself, though the real outflow involves magnetized gas-changing density and motion through an environment far thinner than any terrestrial liquid. Over time, the outflow excavates cavities in the protostellar envelope. These cavities are not perfectly empty. They contain moving gas dust radiation and material along their walls, but they are less dense than the envelope around them, making them easier routes for light to follow. Radiation from the protostar and the warm inner disk can travel into the cavities, scatter from dust along their edges, and produce two faint lobes of reflected or reprocessed light. In infrared observations, the resulting shape may resemble an hourglass with the dark disk and dense equatorial material narrowing the center while illuminated cavities expand above and below. The light does not reveal the protostar directly in every case. Sometimes we're seeing radiation reflected from a wall rather than a clear view of the source itself. The cavity acts less like an open window and more like a dimly illuminated corridor turning around a hidden corner. Viewing angle can therefore transform the appearance of the same young system. Seen nearly along the outflow axis, an observer may look down a relatively cleared cavity and detect more short-wavelength radiation from the warm inner region. Viewed from the side through the dense plane of the disk and envelope, the central source may remain deeply obscured. One cavity can also appear brighter than the other if the system is tilted, because light from the nearer side may travel through less dust before reaching us. A structure that is physically bipolar can consequently look one-sided. This is an important caution when astronomers classify young stellar objects. Differences in appearance may reflect genuine evolutionary stages, but some may also arise from orientation. A protostar does not know which direction the telescope is located. It simply offers a different version of itself to every line of sight. The outflow also influences the cloud from which the star is feeding. By carrying momentum outward, it can stir nearby gas and remove part of the envelope that might otherwise have joined the protostar. This helps regulate how much mass the growing object ultimately retains. Outflows may create compressed shells or knots where local density increases, while elsewhere they disperse material and reduce the supply available for collapse. It is tempting to describe them as either triggering new stars or preventing them, but nature does not require one answer in every region. Their effects depend on geometry, energy, cloud density, magnetic structure, and the presence of neighboring cores. A flow may compress one pocket while disrupting another. It may create turbulence on a small scale, while allowing the larger cloud to remain gravitationally bound. The young star alters its birthplace, but it does not control the entire nebula with a single simple outcome. We have now followed the cloud's hidden story from a starless core to a growing protostar, a rotating disk and two paths being carved through the surrounding darkness. The first escaping light does not mean that the cloud has become transparent. Most directions may remain heavily obscured and the star itself is still unfinished. Yet the cavity's jets and molecular outflows announce that something inside has crossed a threshold. Matter is gathering inward while other matter is being sent away. Light is absorbed in one direction and released through another. The black silhouette has begun to develop an internal geometry that visible images alone could never reveal. But the original title asks what lies behind the nebula, as well as what may be forming inside it. To answer that more literal question, we must travel beyond the protostar, cross the far boundary of the cloud, and allow the hidden Milky Way to return. The far side of a dark nebula does not open into a special hidden realm. It opens back into the Milky Way. Once our imagined journey crosses the final layers of dust and molecular gas, the stars that vanished from the visible image begin to return. Some are relatively nearby. Others lie thousands of light-years farther away. Between them may be glowing clouds, additional dark clouds, old stellar populations, and broad regions of diffuse galactic light. From Earth, all of these objects appear projected onto the same small patch of sky. The nebula stands in front of them like a curtain, but the stage behind it may extend through a large portion of the galaxy. What looked like one black surface was therefore never a final background. It was only the nearest major layer along a much longer line of sight. An astronomical image compresses distance. A foreground star, a dark cloud, and a distant cluster can appear side by side even when enormous spaces separate them. The image records the direction from which the light arrives, but it does not automatically reveal how far each source has travelled. A useful comparison is a photograph taken through several windows on a rainy evening. A drop of water may sit a few centimetres from the camera. A reflection may come from the room behind it. A building could stand across the street while hills occupy the horizon many kilometres farther away. The finished photograph places all of them on one flat surface. The night sky does the same thing on a far greater scale. Nearby dust middle-distant stars and remote structures are arranged together by direction rather than by physical connection. This is why the stars seen around a dark nebula do not form one simple background sheet. Some lie in front of the cloud and remain largely unaffected by it. Others are embedded near its outer regions or belong to the same broad star-forming environment. Many more lie beyond it and appear dimmed, reddened, or completely hidden. To separate these groups, astronomers combine several kinds of evidence. Distance measurements can place some stars before or behind the cloud. Stellar colors can reveal how much dust their light has crossed. Motion across the sky and motion along the line of sight may identify stars that travel together. Spectra can estimate temperature composition and velocity. None of these measurements alone solves every case, but together they begin restoring depth to the flattened image. The background itself may contain more than the individual stars. A dark nebula can obscure glowing hydrogen gas illuminated by young hot stars, making the cloud appear as a sharp silhouette against a luminous region. It may hide part of a distant stellar nursery, or overlap with another molecular cloud farther along the same direction. Toward crowded portions of the Milky Way, a single line of sight can pass through several spiral arm features and large amounts of diffuse dust before eventually reaching the central regions of the galaxy. Radio and infrared observations may reveal layers that visible light merges into one darkness. Different molecular velocities can show that two patches appearing connected on the sky are actually moving separately and may lie at different distances. The universe can create convincing visual relationships between objects that have never met. Even when a bright structure is revealed behind the cloud, its light may carry an older story than the nebula's current appearance. Every photon has taken time to travel. A star several thousand light-years beyond the cloud is seen as it was several thousand years before its light reached us. The dust then altered that ancient signal before it continued toward Earth. The final image combines different distances and therefore different look-back times. These differences are modest compared with the deep history seen in distant galaxies, but they still remind us that a view of the Milky Way is not one perfectly synchronized moment. It is a layered collection of messages arriving together. The dark cloud does not merely hide places. It interrupts light emitted at different times from objects with different histories, all aligned by chance behind the same patch of sky. The literal answer to what lies behind a dark nebula is therefore usually quite ordinary by cosmic standards, more of the galaxy. There may be main sequence stars, red giants, glowing gas, additional dust, compact stellar groups, or simply a long stretch of comparatively sparse interstellar space before the next visible object. What lies behind one portion of the cloud may be entirely different from what lies behind another. The black silhouette creates the illusion of a single concealed scene, but every narrow line through it points toward its own sequence of distances. There is no one object waiting behind the entire curtain. There are many objects separated from one another by light years, and gathered into one apparent background only because we are viewing them from very far away. This distinction also helps us separate two mysteries that have travelled together throughout the documentary. One concerns the cloud's interior, its dust molecules, filaments, cores, and possible young stars. The other concerns the distant light that the cloud blocks. Infrared observations can sometimes reveal both at once, which makes the image beautiful, but the interpretation difficult. A point of light may belong to a protostar within the nebula, or to an unrelated star far behind it. A bright patch may be dust-heated locally, or radiation from a background region shining through a thinner opening. A dark lane may contain dense material, or simply sit in front of a weaker background. To decide among these possibilities, astronomers must combine distance, temperature, chemistry, motion, and wavelength rather than trusting appearance alone. We have now crossed the cloud and found no hidden wall, no missing portion of space, and no single object responsible for the mystery. We found the Milky Way continuing behind it, arranged in overlapping layers that a visible image cannot separate by itself. The nebula remains important because it changes every signal passing through it. It dims stars, alters their colours, absorbs radiation, and adds emission of its own. To reconstruct what belongs inside the cloud and what lies far beyond it Astronomers must place all these partial views together, extinction maps, infrared glow molecular spectra, polarization, velocity and distance. Only then can the black silhouette become something closer to a physical model. Our next step is not to travel farther, but to gather every clue and rebuild a cloud that no observer can ever see from all sides at once. No telescope can carry us around a dark nebula and photograph it from every side. We observe from one small location in the galaxy receiving radiation that has travelled toward us along a limited set of directions. Every image is therefore a projection. Material near the front of the cloud may overlap material near the back. A compact knot can hide behind a diffuse layer. Two filaments separated by a considerable distance may appear to cross, while structures that are physically connected may be difficult to recognize because they extend partly toward us. To reconstruct the cloud, astronomers must combine many incomplete measurements and ask what three-dimensional arrangement could have produced them. The result is not a secret photograph waiting inside a computer. It is a physical model constrained by shadows, temperatures, molecular fingerprints, velocities, distances and polarized light. The cloud remains inaccessible, but it is not beyond investigation. The reconstruction often begins with dust. Visible and near-infrared observations measure how background stars are dimmed and reddened, revealing the amount of obscuring material along different lines of sight. Far-infrared and sub-millimeter observations then detect radiation emitted by the cold grains themselves. By comparing the brightness at several wavelengths, astronomers can estimate a dust temperature and infer how much material may be present. A warmer, thinner region and a colder, denser region can sometimes produce similar brightness at one wavelength, so a single image is not enough. Several measurements are fitted together to separate temperature from column density, as well as the data allow. Even then, the answer depends on assumptions about how efficiently the grains emit radiation, whether their properties change inside the cloud, and how many temperature layers overlap in the telescope's beam. The map grows more informative but never entirely assumption-free. Molecular spectra add the dimension of motion. Each measured position on the sky can contain a spectral line whose frequency and shape reveal how emitting gas is moving along our line of sight. Repeated across the nebula, these measurements form a data cube 2 dimensions describing position and another describing velocity. Astronomers can move through this cube and watch structures appear at different speeds. A feature that seemed like one cloud in an ordinary image may divide into several components. A filament may remain coherent across both position and velocity, strengthening the case that it is one physical structure rather than a chance overlap. Gradual shifts may suggest rotation or organized flow. Asymmetrical lines may be consistent with inward or outward motion. But velocity is not the same as distance, and different processes can create similar patterns. The cube restores part of the hidden depth, not all of it. Polarization contributes a different kind of map. Dust grains are not always oriented randomly. Their statistical alignment with magnetic fields can cause absorbed or emitted radiation to possess a preferred direction. Measurements of this polarized light allow astronomers to infer the field's orientation projected across the plane of the sky. The resulting pattern may follow a filament cross-it bend around a dense core or become tangled where the gas is disturbed. This helps researchers test whether magnetic fields are guiding flows resisting compression or being reshaped by gravity and turbulence. Yet here again, projection matters. A field pointing mostly toward us can leave only a weak pattern across the sky. Several magnetic layers can overlap and partly cancel one another. Grain alignment may also become less efficient in deeply shielded regions. The lines drawn on a polarization map are useful guides, not iron rails installed inside the nebula. Distance measurements help place the cloud within the wider Milky Way. If stars closer than a certain distance show little extinction, while more distant stars suddenly become reddened, the intervening cloud probably lies near that transition. Measurements of stellar parallax can provide geometric distances for many of these probes, allowing astronomers to estimate where separate dust layers begin and end. Large groups of stars can also trace the shape of obscuring material across a broad region, but the reconstruction becomes difficult where few suitable stars are available, where extinction hides the most distant probes, or where several clouds overlap. The cloud has managed to obscure the very lamps needed to measure its depth, which is efficient of it, though not especially helpful. Statistical methods can fill gaps and estimate probable structures, but they cannot turn missing information into certainty. Computer models bring these clues together. A proposed cloud is assigned a distribution of density, temperature, chemical abundance, velocity, and sometimes magnetic structure. Radiation is then allowed to move through that model mathematically. It may be emitted, absorbed, scattered, or shifted in frequency before emerging in the direction of the observer. The synthetic result is compared with real maps and spectra. If the model predicts too much infrared glow, too little extinction, or the wrong molecular line shape, its assumptions must change. This process may be repeated many times, exploring different geometries and physical conditions. Several models can sometimes fit the same observations, creating what scientists call a degeneracy, different hidden structures producing similar outward signals. Independent measurements become valuable because they restrict the possibilities from different directions. A model that fits the dust but fails to reproduce the molecular motion is not yet a satisfying cloud. The finished reconstruction is therefore layered rather than absolute. One map shows projected mass, another suggests temperature, a third traces selected molecules, a fourth records motion. Polarization adds the orientation of part of the magnetic field, while stellar distances place some structures before or behind others. Where these independent clues agree, confidence grows. Where they disagree, the disagreement may reveal changing grain properties, frozen out molecules, hidden temperature gradients, unresolved flows, or an incorrect assumption about the cloud's shape. Science advances not by forcing every map to tell the same story, but by asking why they sometimes refuse to do so. We cannot enter the nebula, walk around a core, or watch its entire history unfold. Yet we can build an increasingly constrained portrait of a cold, moving, chemically active structure suspended in the Milky Way. With that portrait assembled, we are ready to return to the original black silhouette and give the clearest answer we can to what its darkness is really hiding. So what is the darkness really hiding? The clearest answer is less dramatic than a secret world, and more remarkable than an empty hole. A dark nebula hides the ordinary light of the Milky Way, because cold gas and microscopic grains of dust have gathered between us and the stars beyond. The dust absorbs and scatters visible radiation, turning a crowded stellar background into a smooth black silhouette. Behind the cloud, the galaxy continues with more stars, glowing gas, additional dust, and distances that may extend for thousands of light years. Inside the cloud, the answer varies. There may be broad reservoirs of molecular gas, long filaments, compact clumps, dense starless cores, or protostars still wrapped in the material from which they are growing. Darkness alone cannot tell us which of these is present. It tells us only that something stands in the way of the light. What we know comes from several independent kinds of observation. Background stars become dimmer and redder where more dust lies along the line of sight. Cold grains emit their own faint radiation at infrared and submillimeter wavelengths. Molecules produce narrow spectral signatures that identify parts of the gas and reveal motion through the Doppler effect. Polarized light offers clues to the orientation of magnetic fields. Distances to stars help place cloud layers in front of or behind one another. When these measurements agree, the black patch becomes a physical environment with temperature, density, chemistry, and internal structure. It is no longer merely a shape on an image. It is a cold region of the interstellar medium built mostly from gas and shaped by radiation, gravity, pressure, turbulence, and magnetism. The dark outline is only its visible shadow. Evidence also suggests that many such clouds contain the conditions from which stars can emerge. Dense material often gathers along filaments. Some compact cores appear gravitationally bound and may continue contracting. When collapse proceeds, a protostar forms within the surrounding envelope, warming nearby dust and gathering matter through a disk. Jets and wider outflows can then carve opposing cavities through the cloud, allowing some radiation to escape along paths of reduced density. But this sequence is not guaranteed for every dark region. A dense core may remain starless for a long time. It may oscillate around a state of near balance, lose material, be disturbed by its environment, or disperse before a protostar appears. Barnard 68. The rounded darkness we used as our guide remains valuable precisely because its future is not obvious. It shows us that a cloud can contain possibility without yet containing a star. Much remains unknown because astronomy usually gives us only one viewpoint, and a very brief moment in the life of the cloud. We cannot directly watch a core evolve across the immense times required for its fate to become clear. We cannot always determine its complete three-dimensional shape from a two-dimensional projection. Different combinations of temperature, density, dust properties, and geometry can produce similar outward signals. Some deeply embedded sources may remain below the sensitivity of current instruments, while apparent sources can turn out to be unrelated objects farther in the background. The relative influence of gravity, turbulence, magnetic fields, and external pressure also differs from cloud to cloud. Science can constrain these possibilities sometimes very strongly, but it should not replace uncertainty with a more satisfying story, simply because the image looks mysterious, and there is no securely established object that can be crowned the single darkest nebula in all of space. Darkness depends on what wavelength we choose, how much light lies behind the cloud, how thick the cloud appears along our particular line of sight, and how sensitive our instrument is. A nebula almost perfectly black in visible light may glow in the far infrared. A cloud that hides a dense stellar field may seem more dramatic than an equally opaque cloud placed against an already dim background. The phrase darkest nebula is therefore best understood as the beginning of a question, not the result of a universal measurement. Astronomy rarely provides convenient winners in competitions that depend on where we stand and how we look. The universe has many ways to be dark, and not all of them mean the same thing. Return now to the image with which we began, a field of tiny stars interrupted by one smooth black shape. At first it resembled a portion of the galaxy that had been removed. Now the silhouette can hold a different meaning. Its edge marks the gradual arrival of dust. Its center identifies a path where visible photons have been reduced almost to nothing. Hidden within may be cold molecular hydrogen, icy grain surfaces, slow chemical reactions, internal currents, magnetic structure, and perhaps a core balanced near the threshold of collapse. Farther behind it, the Milky Way continues unnoticed, its stars still shining, even though their light cannot complete the journey to our eyes. Nothing has vanished. The view has simply been interrupted. Perhaps that is the quietest lesson of a dark nebula. The universe does not reveal all of itself in visible light and absence. in an image is not always absence in space. Sometimes the most informative region is the one that seems to show nothing. A shadow can measure matter. Missing stars can draw a map. A faint molecular line can reveal motion in a place no spacecraft has entered. And uncertainty can remain after all the measurements have been gathered, not because science has failed, but because the cloud is real layered changing and seen from very far away. Outside your window, the night may also contain dark spaces between the stars. Most are simply directions from which too little visible light reaches your eyes. A few may point through distant dust that hides more of the galaxy beyond. You do not need to identify them tonight. You do not need to remember the names of the wavelengths, molecules, or forces we followed through the cloud. It is enough to know that the darkness above is not one simple thing. Some of it is distance, some is emptiness, some is matter standing quietly in front of light. And inside that matter a future star may be forming, or a cold core may remain peacefully starless for ages still to come. The black curtain can close again now. The infrared glow fades from our imagined instruments. The spectral lines grow quiet, the hidden filaments disappear, and Barnard 68 returns to a small dark shape among the stars. But it no longer feels like a whole. It is a place, cold, complex, unfinished, and connected to the same galaxy that surrounds the sun and the room where you are resting. The darkness was never the absence of a story. It was where the story had learned to hide its light, and for tonight that is enough to know.